So this is the smallest number in the first column. This is the smallest number in the second column. Right? So if this is smaller, that means the second column has the smallest overall element. Right? So that's interesting. So that's telling us the column. Right? So of course, column is just a variable name, but it's a descriptive variable name. Whatever this variable contains is the column that contains the smallest value, because it's basically which element, and the element number in small c refers to which column we're in, because the original min function operated on a column-by-column basis. Okay, so now we know which column the smallest element is in. So now let's look at this other vector, LOCC. Recall that LOCC says, okay, this is the row, right, of the smallest element in column 1. This is the row of the smallest element in column 2. Right? Well, so now we know it's in the second column that contains the smallest element. Right? So we're concerned, though, about which row we're in that column. Because in that column, which row we're in, well, it's the smallest overall. So that row in that column is what we're looking for. So notice if we say LOCC of column, it'll say, okay, this is which column or which element we want to be in this vector LOCC. So therefore, which row smallest, well, is going to be 2 from here. Okay, so we find out row 2, column 2 has the smallest element. Right? And there's a lot of ways to do this. You can try this with matrices where it's maybe not row 2 and column 2 to really see the difference, make sure that this is working, and make sure you understand why this works. Right? And so then one more topic we want to hit is basically two stats functions, the mean and the median. Right? So mean is the average. You just add up all the numbers in a vector divided by the number of elements. In a matrix, it works by column. Right? So if you take the mean of a matrix, you get a vector back, the average in each column. Well, if we take the mean of this vector, the resultant vector, well, think about it. It's, let's say there were 5 elements in each column. Take the mean of these, they all have the same number of elements. So you will, in fact, get the overall mean. Right? So you can say, for a matrix, take the mean of the matrix, and that's the overall average of all elements in the matrix M. Right. With median's the middle number. Right? So let's see, we had 4, 7, 3, 6, 9. To find the median, we could basically just say 3, 4, 6, 7, 9. Put them in order, in ascending order. Find the element in the middle. If there's an odd number, or if there's an even number of elements, take the average of the two closest to the middle. Okay? So here the median would be 6. And so median of a matrix gives you the median in each column. Note, however, that median of the matrix does not find the overall median of the matrix. Why is that? Oh, well, there's something interesting going on. I'll give you a basic counterexample. Here, if we have this following matrix, 199, 100, 2, 2, 97, 198, 100, found the median of each row, 99, 2, and 98, and found the median of this, we would say, oh, the median, I guess, is 98. However, we notice this is not the case. If we write all the elements of the matrix in order, 1, 1, 2, 2, 97, 98, 99, 100, 100. Right, 2, 4, 6, 8, 9 elements. So the number in the middle is actually 97. So median of M does not find the median of the matrix M. And you can think about that in terms of basically distributive property. However you group the elements for the mean, as long as there's the same number in each group, you can take the average overall, and it'll be the same. Median is not distributive in that manner. So, okay, you might be asking, well, how do you find the median? Well, there's another trick in math. There's a trick where if you say M all the elements, it'll take the matrix M and return it to you as a vector. Oh, so great, we can convert a matrix into a vector. Let's say the median of that vector will indeed give the overall median. So this is how you find the overall median. Of course, this works for mean and all the others. It works for sum. You could say sum after converting it to a vector. That works too. Okay, so again, always think about really carefully what you're doing in computer programming and make sure it does what you think it's doing. And we have one more slide. What we're going to do is look at the sort function. Okay, and sort, in a vector, sorts the elements in ascending order. So, great. So the thing is, it operates by column with a matrix. So in this following matrix, if we sorted it, we would get 5, 7, 8. So sort the first column, and 3, 4, 6, sorting the second column, and then 4, 5, 9. Right? So if we wanted to sort everything overall, we would first convert it to a vector, and then sort it, and we would get basically a giant vector in the ascending order of all the elements in that matrix. So notice, so we can sort the columns. Well, how do we sort the rows? I'll give you an example of how we don't sort the rows. We don't use the function sort rows. So there is a function called sort rows. It just doesn't do what you think it does from the name. Sort rows is like alphabetizing. So what it's going to do is keep each row together. So these are all, each row is a solid block. And it's going to go order them first, starting with the leftmost element. So it'll say, okay, 5 is the smallest, so keep that row together, make it first. 7 is the next smallest, keep that row together, make it second. 8 is the next. Right? If there were two elements that were the same in the first column, then it would look at the second column to determine which comes first, which has a smaller element in the second column. Right? So it's literally alphabetizing, but using numbers. All right? So sort rows is like alphabetizing. Sort sorts each column individually, and you'll just have to hang on to the next lecture to see how we sort the rows, in the same way we sort the columns. And two quick functions I want to show you before we end the lecture: flipUD and flipLR. If you give it a vector or matrix, they flip the matrix up to down, flip the matrix left to right. Very useful functions. So just get to know them, play around with them, and of course we have to end with a joke. It's from XKCD, which is one of the greatest webcomics. And so, if you've never seen this before, this is a rotational matrix for 2D vectors. It's a 90-degree rotation. So, yeah, hey, it rotates it. How funny! Ha ha! Right. And I'll see you next week. Please feel free to come to my office hours or any of the TA's office hours if you have questions.